Okay, here we go. Problem number 1 in lesson 8. We're going to show that 2x plus 5 times x plus 3 is equivalent to all of this. And so I drew my diagram here. This part across the top is my 2x plus 5. Here is my x plus 3. It might be helpful to put in those plus signs there too if you want. And then as we go through and fill in the boxes, 2x times x is going to be 2x squared. X times 5 would be 5x. 2x times 3 would be 6x. And 3 times 5 is 15. And so now I'm going to look for like terms. I see some like terms right there. And so my answer would be 2x squared. And then I'm going to combine my like terms, 6x plus 5x. That's going to be 11x plus 15. So yes, it is the same as 2x squared plus 11x plus 15. In number 2, you can see that A matches with 4, B would match with 3, C goes with 1, and D goes with 2. And let's work through A just to review how to multiply these binomials. And so just remember that it's using the distributive property over and over and over again. And so I'm going to start with x. X times x would be x squared, and then x times 6 is 6x. And then 2 times x would be 2x, and 2 times 6 would be 12. And I do have like terms right there in the middle, and so I'm going to combine those. So I end up with x squared plus 8x plus 12. And you can see that that does match with 4. In number 3, choices A, D, and E are all the same as x squared plus 4x. I did some color coding and wrote out the work for each of those, expanding them out and showing how you get x squared plus 4x in each of them. D is probably the one that was tricky. So I wrote this out. X plus 2 squared means x plus 2 times x plus 2. And if I use my distributive property over and over and over here, here's what I get in those parentheses. I would combine my like terms, 2x plus 2x to get 4x, so that's right here. And then I'm subtracting 4 from all of it. I really don't need the parentheses at this point, so I rewrote it here. And then the numbers at the end would just be 0. 4 minus 4 is just 0. And so I end up with x squared plus 4x. E is just showing you that it doesn't matter if x or if your multiplication is switched around. You could still do the distributive property, drawing those arrows, and you'd still get x squared plus 4x. Number 4, explain Tyler's mistake. Tyler's mistake happens right here. 2x times 5 should be 10x. It looked like he tried adding 2 plus 5, but these are not like terms, so we need to multiply and get 10x. So to do that correctly, I did it with the diagram here. You could also do it just using your parentheses and distributive property. Remember that the diagram is doing the distributive property over and over again. It's just organizing it for you. I do have some like terms, 10x plus 3x, and so I get 2x squared plus 13x plus 15. Okay, number 7 here, explain why negative values are not included in the range. I gave an example of a table here. I hope your explanation is more in words than mine, but you can just listen to what I'm saying. There are no negatives in the range, which is my possible y values, because I'm squaring x. And no matter what number I take, if I multiply it by itself, I'm always going to get a positive number. So for example, if x is negative 2, that's going to be negative 2 times negative 2 to square it, and that's going to be a positive 4. So no matter, even if I have negative values for x, when I square it, I'm still going to end up with positive values for y. Also, if I graph it, you would see something like this. Okay, and it's showing you that all of your y values are positive. There are no y values that are negative. Okay, number 1 in lesson 9, you are writing them each in standard form. You could have done the diagrams if you'd like. I chose to do the distributive property, so you can see my arrows. And for number 1, I end up with x squared plus 3x minus 4. For number 2, we get 6x squared minus 5x plus 1. Pause the video if you need and look over my work using the distributive property, and let me know if you have any questions on this one. Okay, number 2 in lesson 9. Is the expression in standard form? Yes, it is. Your book shows you that standard form is when it's written like this, when there's numbers in there for A, B, and C. the expression we have up here is a little switched around, but that's okay. You know, as long as we could rearrange it and write it in standard, or in this form ax squared plus bx plus c, which would look like that, then we can say it is in standard form. So it's okay if the terms are switched around a little bit, just as long as the positives and negatives all continue to work. It is still in standard form. And number 2, is the expression equivalent to x minus 4 times x minus 2? Explain how you know. Yes, it is. And my explanation is really shown here with my work. If I multiply everything out using that distributive property, I would end up with x squared minus 6x plus 8, which is the same thing as the expression up there. Terms are switched around a little bit, but that is okay. In number 3 here, C is the only one that's written in standard form. A, B, and D would all be written in what we call factored form, because there are terms that are being multiplied by each other in those. C is the only one where every term is being either added or subtracted, so that is the one in standard form. In number 5, A is the correct answer. A is going to tell you the distance fallen in feet as a function of time. Remember that 16 is that acceleration due to gravity, because when things fall on Earth, they speed up at a rate of 16 feet per second every second. C is maybe the other one that maybe caught your eye. This one would tell you the height off the ground if it started at 180 feet. But it's not going to tell you the distance fallen. It's going to tell you how high it is off the ground. So that's just kind of a small distinction there to pay attention to. And in number 9 on Unit 6, of course I picked this question because of what's going on in the world right now. But if you're looking at this data, an exponential model would be better. If you graphed it, you would probably see that curve as well. But another way to look at it is to look at the growth factor. Each time, it looks like we have a common growth factor of somewhere around 1.4. This is more real life data, so it's not going to be perfect, but it's close to that 1.4 range. And so that's your reason for an exponential model. It has a common growth factor of about 1.4.